there any questions on the homework? What in the call you Virginia? Victoria. All right, number 6. X is t squared plus 2. Y is t squared plus t. So we're looking for a tangent line on this curve to the curve that passes through the origin. Okay, so let me give you a hint and let you take it from there. So we got a curve. I don't know what, actually I do know what it does, but it doesn't really matter. Got a curve out here, and somewhere is the origin. Let's say it's right there. So it looks to me like there's a point about right there. So there's a line that's tangent to the curve that passes through the origin. So they're asking us to find that line. The curve does not go through the origin. X can never be less than 2. But is there a tangent line somewhere? I mean, there could be more than one. So here's my advice. Because they're asking you to do it, believe that such a point exists. Okay? And now I need to, I don't want to call it T because T describes all of the points on the curve. So let's just give it this very own special name, wherever it is. And we don't really know where it is. I just drew this curve and let's think about it. So assume that the point that we're looking for where the tangent line passes through the origin, just give it a name, call it A. And now what we're going to do is solve for A. Okay, we can find the equation of the line. The equation in terms of A. I'll do one more thing, that is, for a line, we need the slope. Well, what is the slope? It's dy dt over dx dt. But we want the slope at this point, so we're going to plug in A. And so I can write in an expression, 2a plus 1. That's the slope. I can find the x and y coordinate by plugging A into those functions, right? And then I can write out the slope, point slope form of the line. I know that line has to pass through the origin, so I know when x equals 0, y is 0, and now I can solve for A. All right? So write the point slope form. Because we know it passes through the origin, that's what makes this line special. I can plug in the coordinates, and it makes the equation true. And the graph of an equation is all of the points that make it true, right? So we know the origins on it, and solve for A. Every problem I see, you get a quadratic equation. When you finally simplified it, it takes a little bit of effort, but it's all basic algebra. And it doesn't factor, so use the quadratic formula in my advice. And I think this problem asks for the exact answer. So let's say for somebody's problem who is in my office today, the value of A was 6 plus 2 square roots of 3, I think. Okay, you have to input the answer like that. Don't approximate it. I mean, it asks for the exact value. So if you approximate it, I mean, I didn't try approximating it. I just did what it told me to do. And it said it was perfectly fine. Of course, you could write this. I don't think you have to do this. So you could write that as 6 plus the square root of 12. I don't think you have to simplify the expression. But you do need to enter it in exactly.
So if you write it in point slope form, you write y minus 0.
Minus a squared plus a. No, we don't know that. This is the point that I can focus on to come up with the point slope. Find the slope there, find the coordinates there.
Okay.
Okay, the slope out here, I mean, it's the same, but it doesn't relate to the points on the curve. This is just some point out there. Could be any point. Yep. It's kind of nice they gave us the origin. Okay, anything else? All right. So everyone watched the videos, the lecture, 6 examples. The first 3 are pretty trivial, then they got pretty interesting. And so we're going to pick up from where those kind of left off. I want to talk a little bit about the polar function. Particles of theta. We never ever think of theta as a function of r. Just, you know, we've gone by perfectly fine without polar coordinates until now. The only reason we're showing them now is that some problems get a whole lot simpler. And the ones that get simpler, and never ever do we think of theta as a function of r. We can think of y as a function of x or x as a function of y, right? We've done good work with both of those, but we don't do it here. A polar function is where r is f of theta. And we think about it a little bit differently. A function, if y is a function of x, then we imagine a curve that moves from left to right. And if x is a function of y, we imagine a curve that goes from bottom to top, right? Well, how do we think about these? Well, remember, theta is some angle going around the origin. So we picture these guys as a curve that moves around the origin. As theta increases, the distance r, it changes along with theta. What happened? Fashion is so, you know, here is I draw that. For some angle theta, here the distance, that point is f of theta, r equals f of theta. And so we picture these polar functions as sort of moving around the origin. And some people call the origin in polar coordinates, they call it the pole. Maybe because of that very reason, it's like a pivot point as theta goes around. So for example, a real simple function, r equals theta. It's simple algebraically. It's not so simple geometrically. Let's use only theta greater than 0. Actually, we can let it be equal. So when theta equals 0, so is r. So this curve starts at the origin, at the pole. And then as theta starts to increase, so does r right along with it, right? And so theta is moving through the first quadrant, and the bigger it gets, the further we get away from the origin. When theta has gotten completely through the first quadrant, pi over 2 is about 1.7. The point is 1.57. The point is that far away from the pole. So maybe there's pi over 2, and it just gradually gets there. And then we get pi units. By the time we make it completely through the second quadrant, and then we need to be down at 3 pi over 2, and then we need to be at 2 pi, right? So, and I could even keep going, and this curve just keeps, what's a good word for what it does? Spirals, yeah. Keeps getting bigger and bigger. And you know, we never saw anything like that with rectangular coordinates. Maybe that's not so important, but it shows how completely new things can be discovered by a pretty simple function, r equals theta. A better example, better in the sense that it's more important, it's more useful. Let's just think about circles. I think we can agree those are important curves. We study a lot of things that are circular in shape. In rectangular coordinates, it's pretty nasty. So we're going to pick a radius of A, and the center is at the origin. Focus on that sort of coordinates. It takes 2 functions, and both of them are complicated. Functions that we don't know the antiderivative for just looking at it. We know how to figure it out. We learned the technique. That's functions of x. I could also use functions of y where I get the left and the half side, left and the right, not the top and the bottom. We improved that a little bit in parametric. I think the best way to think of it is A cosine T. A sine T. I could move the sine and cosine around. It would just change the orientation, not the actual curve. That's better. Those, it still takes two functions, but they're not as complicated as these. They're easier to understand. And then we go to polar, and what is the equation here? It's a constant. A circle of radius A centered at the origin is a collection of all of the points that are A units away from the origin. That is, the distance away, R is constant. So you can see vastly superior in terms of algebraic complexity to illustrate a circle centered at the origin in polar coordinates. Probably about 80% of the time we use polar coordinates is because we have a circle. And you know, if we're a physicist, we think we're studying this object that's a circle, and then what I want to do is introduce it into the plane. I can do it however I want. Well, if I can do it, you know, given other constraints I have to worry about, I want to put the center at the origin, and then I can use a constant function if I can work in polar coordinates. A parabola, pretty much no parabola has a pretty polar form. They're all awful. Lines, awful, unless they pass through the origin. And then it's just theta equals a constant. If they pass through the origin, then all of them have the same angle, right? You try to find it in polar coordinates. So some curves are absolutely amazing in polar and some are awful. And if we're, especially in Calc 3, where you'll use polar coordinates in 3 space, you'll add on a z, an up and down coordinate. And you need to recognize, like, when should we do polar or not? And circles, lines to the origin, all good things. There are other things too. A lot of the things are kind of exotic, like this. We never saw before because they're not conducive to being expressed in the other systems. We'll look at a few of those examples today, actually. All right. Are there any questions? 6 brave people show up to class. All right, so we're not talking about like the basics. You got that in the videos I pointed you to yesterday. I showed you at the beginning of class some practice problems if you needed. I think you should find most of those pretty easy. What I want to do today is talk about some calculus applications of polar coordinates. And we'll start with an example. I want a graph of polar function. I want to show you how I think about it. And I think Nick did some of this. I didn't watch it all the way through, all of the examples. And so maybe, you know, there will be overlap. I hope so. And then once we've got the curve figured out, then we'll talk about some calculus information we can get from the curve. So we'll draw the curve, we'll pause, talk about calculus, and then apply the calculus to the curve. In the morning class, I thought I could do 2 of them, but it turned out I was wrong. I only did 1. I wanted to pick different examples. I recorded the morning class, but it didn't go so well. Some technical glitches. So the example I did in the morning class, I actually posted a photograph of it. It's one of those I showed you. And so we'll do a different one here. It's actually pretty similar. A little bit different. Graph R equals 4 minus sine theta. Now, we absolutely can pull our calculators out. We can change the mode, graphing mode, to polar. It might be in rectangular, it might be in parametric. Use both of those, right? And we can graph here. What I want to do is like take step by step, work it out without a calculator. So we understand how these polar functions get their values and how we illustrate those values on the graph that we come up with. All right. So, and one of the things that went wrong in the morning class is I found a polar graph paper. You probably saw it in high school. And I thought I could show the graph paper interactively with the problem, and I just didn't think through how Zoom works, and it just was like for 8 minutes, a blank picture of polar graph paper. So I'm not going to use it. I'll just draw my very best polar graph paper. Just a bunch of concentric circles. One, two, three, four, five. I actually need one. Nope, 5 million. All right. So there's polar graph paper, concentric circles. Typically, graph paper has some angles identified. So for this one, we're going to need pi over 6 in every quadrant. This would be 5 pi over 6, 7 pi over 6, 11 pi. But graph paper has lots of angles. The one I pulled up, it actually was all multiples of pi over 12. So I don't want to clutter up the picture. So we'll just draw the ones that I think we're going to need to work this thing out. All right, the range of R. Tell me the values that R could take on, like the smallest and the largest. What's the smallest thing that R can be? 3. And the biggest? 5. Do you agree? For all thetas, R is between 3 and 5. So I do that observation, and then I know how to like measure in my polar plane. Like these circles, they could be 1 unit apart, or 4 units apart, or a third of a unit apart, whatever seems reasonable. And because there are 5 of them, and the function gets no bigger than 5, we're just going to let each one be 1 unit further away. So the radius of these circles, 1, 2, 3, 4, 5. In this particular function, the whole graph is between the circle corresponding to 3 and the circle corresponding to 5. R values, the distance from the origin, that's what R means, always between 3 and 5. So let's just shade out. Here is the circle of radius 3, and our graph is never going to go inside. And of course, 5 is the biggest one, so there's nothing really to shade out. I guess we could say we can't go out here anymore. Got to stay inside that circle of radius. Okay, and now let's take a look. I like to analyze it by quadrants because the sine function is real predictable in each quadrant. So we'll make a little table here. We'll have a table for quadrants, for theta, for sine theta, and R. Because the period, we're not changing the period, so it's 2 pi. If we can figure out in all 4 quadrants, we'll know everything. In fact, we can probably just think like, let's do this for the first revolution, and nothing's going to change beyond it. So in the first quadrant, theta goes from 0 to pi over 2. Sine goes from 0 to 1. So R, sine starts out at 0, plug it in, I get 4, and then sine gets up to 1. We end up at 3. I want to color code this. So the first quadrant we're going to do in red. So we start right here, 4 units away from the origin. We end up here, 3 units away from the origin. And throughout the first quadrant, the curve just slowly creeps back. It's a 3. Now, I like to do a quick calculation just to help me draw a more accurate graph. The sine function, notice I put pi over 6 on here because the sine of pi over 6 is easy to work with. What is it?
Pi.
Yeah, it's 1/2. So when theta equals pi over 6, r equals 4 minus 1/2, 3.5. And so, there, we need to go through that one. Oh, sorry. We need to go out halfway. I don't have half circles I did in this example in the morning class. We need to be halfway between the circles, not pi over 6. Again, then we just draw the best graph we can. Gradually getting sucked into that circle radius 3. Sort of like. It looks like I slipped inside the circle of radius 3. That doesn't happen. We'll know in our heads it doesn't happen. Quadrant 2, theta goes from pi over 2 pi. The sine just retraces its path back. 1 back to 0. And therefore, we left, we'll do this one in green. Our function ended off at 3, so it's going to start at 3, and it's going to work its way back to 4. And again, there's this halfway point. We're going to end up here. And the halfway point at 5 pi over 6. Pi over 6 into quadrant. Sort of like that. Those curves are a mirror reflection across the y-axis. May not look like it, but we know it's true. We'll convince ourselves. All right, quadrant 3. Theta goes from pi to 3 pi over 2. Sine goes from 0 to -1. We left off at 4. We'll do this one in blue. And 4 minus -1 gets us out to 5. So we start here where the curve left. We're going to end up there and got this halfway point again. Halfway set. So we'll draw the best curve we can. Gradually working our way out. And then I think it's fairly obvious that just going to retrace that. Something like it's like a not quite circle. Oblong. Circle. Only goes 3 units up, 5 units down. Questions? Scott?
So on the bottom of the graph on the right, isn't theta supposed to be pi over 6?
Yes, it is. The calculations are right. Good spot. Some of you have been worried about that for a little while. Victoria?
So when we're graphs like this, we just choose like another angle.
Yeah, and there's usually an angle that makes the arithmetic easy. For cosine, we pick pi over 3, not pi over 6. For tangent, we pick pi over 4. Tangent of 1. Right? All right. So, nope, let's start calculus. I have two topics. Could be three. If I looked at the homework before I taught the morning class, there would be three. Or maybe there would be two different ones, but I didn't, so you're gonna get the same thing in the morning class. Because it's calculus, of course, we want to know the slope of the tangent. Now, in Calc 1, we learned, well, the slope of the tangent is the derivative. Evaluate the derivative, get the slope of the tangent. That's exactly right. If y is a function of x. Because if y is a function of x, the derivative tells us the rate of change of y. And that's what slope is. Change in y over change in x, right? But slope is not change in r over change in theta. We don't know what that tells us. Maybe we could figure it out. I think we could come up with a way to interpret it, but we're not going to because no one ever thinks about it evidently. So what I want to know is like, I have a curve here, and sure enough, at every point, there's a tangent line. Probably I can find the slope of that tangent line. But it's not dr d theta. It's the derivative in Calc 1 because the change in y is how we calculate slope. So there are two ways I can do this, Barry. I've never done the second way in my life. I'll make it the first way. I could like just go back and analyze directly from the polar equation how I can get from that polar function to information about the slope. I don't know how to do that. I've never done it. Like I said, there's another way we can do it. I can express every polar function in parametric form. And we know how to do that if it's in parametric form. So we can just use what we learned on Monday. Okay, so here's what we're going to do. Function r equals f of theta. Hopefully I can spell. Can be written in parametric form. Remember, parametric form means a function that tells me how the x coordinate behaves, and another function that tells me about the y. Both of them in terms of some other variable. So we know I can convert between polar and rectangular by these formulas. You saw them in the videos I posted. Very important. There's about a 98% chance you'll need to know those on the exam next week. So I can replace the r here with the function that I want, and then I will have a parametric form for those points, an equation for x and an equation for y. So we're going to replace r with f of theta, cosine theta, f of theta sine theta. The parameter, it's not some generic unknown parameter t. It's the angle we know because it comes right straight from our knowledge of polar functions. So this curve is the same as this one. And so I can use what we learned on Monday to find information. dy dx is dy d theta. Need to use the product rule here. So we'll take the derivative of the first function times the second plus the first function times the derivative of the second. And do the same thing down below. F prime of theta sine theta minus f of theta cosine derivative of sine and minus cosine. Maybe we can ask for a prettier, but we have a form, and in general, can't really simplify it. Depends on the function r, what we can do with it. So let's try this problem. Find the slope change, the slope of the tangent, rate of change of y with respect to x. At x equals, well, let's do pi over 4. For the same curve, the one we just did graph. So pi over 4 is going to be about there. So we're looking for a negative number. Maybe -1-ish. Let's see. All right, our function. Sine to that. And we need f prime, you can see in the formula, minus cosine. So f prime of theta minus cosine pi over 4 times sine plus f of theta 4 minus sine pi over 4 times cosine pi. Numerator. The denominator f prime minus cosine pi over 4 sine pi over 4 minus f of theta 4 minus sine pi over 4 cosine pi over 4. And now we have an arithmetic problem. Cosine pi over 4 and sine 1 with square root of 2. Distribute. That's right, minus 1 over the square root of 2. 1 over the square root of 2 minus 4. 1 over the square root of 2. Minus minus plus. Pick the super nice angle. Or we deserve something nice. I do it right, Victoria, you're looking carefully.
Wait, cosine of
So pi over 4 cosine and sine are equal. Some of you may remember square root 2 over 2. Some of you may remember 1 over the square root of 2. Those are the same. Whichever way you think about it, it'll work out perfectly. Doesn't matter. So, minus a half plus 4 over the square root of 2 minus another half. Down below, minus a half minus 4 over the square root of 2 plus a half. 4 over the square root of 2 minus 1 over minus 4 over the square root of 2. Right, the halves cancel down below, they stack up above to get me a full 1. Ugly answer. Let's multiply top and bottom by square root of 2 over 2. I don't know if you're a high school teacher or if you figured out to do this to simplify fractions, but you surely know by now that it's my preferred way. It makes life so easy. So in the numerator, I get 4 minus the square root of 2. Begging your pardon, yes, that's what we get. And down below we get -4. And then let's absorb this minus sign up there. Just, I like pretty answers. We can, without sorting. And that's our answer. A positive or a negative number?
Negative.
Do we like getting the negative number? No? Well, earlier I drew approximately the tangent line. Looks like I almost drew it at 5 or 6. But we observed that we wanted to be negative. And I said sort of maybe -1 ish, maybe. It's not -1. It's a little bit flatter than -1. Okay, questions? So the slope of the tangent to a polar curve, there's our formula right there. All right, second application, interpretation calculus to polar coordinates. Again, we'll use that curve, it's on the board. But first, let's develop it, and that is area. I'm gonna put under in quotes. Polar function. I'll show you what I mean. So think about polar functions as moving around the pole. Theta moves counterclockwise, and for every theta, we have an R value, a distance. And let's say I want to find the area from some angle alpha to some other angle theta. So the area, I'll sketch in blue. Solid. So under actually means between the function and the pole. Okay. If rectangular coordinates, we could approximate the area using rectangles. We partition the x-axis, we get these nice rectangles, all of them the same width, delta x, then we could find the height based on the function. Well, we can't do that here. There's no obvious way to fit rectangles under that curve. If again, we think of r as a function of theta, if I'm going to partition theta, just like we partitioned x, y being a function of x, then I get these radial lines coming out of the origin. Right? And so what I'm going to do is approximate the area on one of these guys. Let me just pull him out of there so it's not so cluttered. So there's one of those sections I pull out. The curve is doing something up here. Who knows why? Whatever the function tells us to do. We don't know how to get the area of that region, but we do know how to do this. The area of a sector of a circle. So take a circle, a sector is we're going to take a little pie-shaped piece out of it. And what we want to know is how big the angle is that generates this piece. So the circle is radius r. And I take the slice out. The area of that slice is 1/2 r squared theta. Theta must be measured in radians. One of the reasons why we love radian measure. We would have a nasty looking expression if we were forced to measure theta in degrees. This is easy to derive. Can you believe if I double the angle, I double the area? Does that make sense? If I cut the angle in half, cut the area. So the area is proportional to the angle. And then I can take like the whole circle. The angle would be 2 pi. And I can set up the proportion and derive this. It's not complicated. If you're convinced that the area is proportional to the angle theta. And I think you all were nodding at me, so I think you are. All right, so here's what we're gonna do. I can approximate the area of this guy with a sector. That's not a sector. Whatever that function is doing, who knows? But I can approximate it with a sector. And so what we're gonna do is pick some angle in between here. By the way, this angle comes right straight from our partition. We'll call it delta theta. Chop it all up, and each one of those has an angle delta theta. We'll pick one angle that lies inside here. And we're going to call that angle theta I star. This is the ith part of the partition. And then green. To approximate that area with a sector of a circle. So imagine the circle going sort of like that. You got a circle moving around this center point. Base of I, the area in the ith part of the partition, is approximately equal to the area of that green sector, which is 1/2. What's the radius of that sector?
F of theta.
F of theta, the theta we chose. Did I not give it its full name? Oh, yes, I did. Theta I star, and because of the sector, we got squared. And what is the angle for that sector?
Theta.
Theta. So theta is the angle from the positive x-axis. But we don't want to go, we just have this little slice we cut out. Delta theta, absolutely. It's labeled delta theta. And not only is it delta theta, we're thrilled to see it show up, because why? I didn't say the magic words. Let me back up a little bit. What calculus tool do you think we might have to use to get the area? Integration. Yeah. And so I'm calculating something I've never tried to calculate before. I don't know a formula for it. So if I'm going to find a formula, I have to find a Riemann sum estimate of it. And if I can do that, then I know I can convert that to an integral. Okay? And all the ingredients are here. We have a function of a point on the interval times delta theta. So the total area is going to be approximated by summing all of those guys up. We have n parts to the partition. So I will move us across. Yeah, star goes there, we'll square it, delta theta. We have, without even trying, we have a beautiful Riemann sum. You know, we couldn't really finish Calc 2. About one more chance to see a Riemann sum, right? We did it. And in the limit, it becomes, if we eliminate the error, I guess we need to convince ourselves that if we chop it up to finer and finer pieces, does the error go away? Right now, we're missing this little chunk of area, and we're adding this piece in, so it's not quite right. As those pieces get smaller and smaller, you feel like all the error is going to go out. Yeah, it seems pretty reasonable. And therefore, we get the area is exactly equal to the integral from alpha to beta, shown in this picture. The function, you know, next to the delta x, between the segment and the delta x, it's 1/2 f theta squared. So whether you believe in Riemann sums or not, whether you remember the first thing about them or if you remember everything about them, here's a formula. You can use a formula no matter what. There it is. All right. So Let's turn an area problem out of the function we drew earlier. So for the same function, find the total area enclosed. So the function was minus sine theta, is that right?
4.
4. There's the graph. The area is the integral. For the total, we just want to go all the way around the circle, 0 to 2 pi. Period is 2 pi. We're not changing the period. So I'll post an example where we are changing the period. I'll post a picture of it, maybe a video of a picture of it. And then our function, our formula, we have a 1/2. Which comes along for the right, and then we take our function and we square it. Take the 1/2 out. Unfortunately, can't really get an antiderivative taking advantage of the square. There's the derivative of the inside is cosine, right? And there's no cosine there. So we have to square it out. 16 minus 8 sine theta plus sine squared theta. Okay, are you with me? The antiderivative of 16 is
16 beta.
16 theta. Remember, we got that 1/2 out front. The antiderivative of sine theta is
Cosine theta.
negative, so let's flip that sign. And sine squared, what do we do with that? Oh, wait, I asked you to memorize that. So we have it memorized. It's 1/2 theta minus 1/2 sine 2 theta. Here. So we memorized it. I know you did because I asked you to. Like the top one. This is gonna, most of this is gonna collapse because we have super nice angles, 0 to 2 pi. I posted a picture of a problem where we did not have nice angles. And you can kind of fight through +8. What's the cosine of 2 theta? 2 pi.
1.
1. So good. We have 1/2 times 2 pi. The sine of 4 pi,
0.
0. Let's leave the 1/2 out of everything. What survives when I plug in 0? Only one thing does. Cosine. So -8. Cosine of 0 is 1. Sine of 2 pi is 0. So we get 1/2 32 pi plus 8. What? 8 minus 8. So plus pi. About 33 pi over 2. Feel like a good answer. It's a quick way we can get a really rough check on it. We know the whole graph is contained inside the circle of radius 5. In fact, it uses up most of the area. That circle has 25 pi units. Radius is 5 pi r squared. So 33 halves is a little bit less than 25. So really quick, I mean, it doesn't prove too much. We could also, the whole graph is outside the circle of radius 3. That's 9 pi. 9 pi would be 18 pi. So definitely our answer is between the two extremes, so that makes us feel pretty good about it. We'll go with it for now. Any questions? All right, I'm gonna post some extra problems. Be sure you check them out. Problems that I work through, just to give you more variety. And then we only had time to do one in class. That's not enough. The homework assignments pretty lengthy. Plus there's that extra one. That's not calculus, it's just about polar curves in general. All right, we'll see you Friday. The very last day of class.